Good morning, everybody. Welcome to episode 9 of AlgorithmsThread. I'm your host, David Harmeyer, and today we'll be talking about treeps. Treeps are a really cool data structure. They are similar to segment trees, but they can do some more powerful things. And we're going to talk about what those things are and how you can implement them today. As usual, we're going to start with some prerequisites. So the thing you definitely need to know in order to be able to get anything from this lecture is kind of what a tree is, some basic tree vocabulary, like what a subtree is, stuff like that. And if you haven't yet, I would definitely recommend looking at my tree basics video. There's a Codeforces blog post on it, and also it's a previous algorithms thread on my channel, algorithms thread episode 8. And in addition to knowing trees, you don't have to know this, but it would be pretty helpful. If you know segment trees and lazy propagation, you'll get a lot more out of the second half of what we're going to learn today. Like I said, it's not totally necessary. You might be able to figure it out otherwise. But I would recommend just watching the segment tree video that I made. I explained lazy propagation in that, and you should be able to get some good practice in with the problems that I made. Again, just like the tree basics video, I made a gym contest, which will be published shortly after this lecture goes live. So if you are seeing this on YouTube, as soon as it's over, you should be able to try some problems. And I definitely recommend doing that because it'll help you practice to make sure you're really absorbing the material. You might think you understand it, but once you finally have to code it, then it's kind of like the real test to make sure you could do it in a contest. I made 5 unique problems for this gym. They're not like used in previous sets. The same ideas may have appeared before because they're relatively simple. I don't want to make something super, super complicated. But they use different tricks that you may not have seen before, and I think they're pretty good problems. One of the problems was a very challenging problem, so I split it into like 3 different subtasks. So there's an easy version, a medium version, and the hard version. All 3 are possible. And for all of the problems, I would recommend you solve them using Treaps. You might be able to find other solutions as well, but yeah, I recommend doing them. All right, so first, what is a treep, and really, why do we care? So there's a common problem, which we have seen before, which is, let's say you have some array, and you want to do some things to the array. So in the past, we've used segment trees to do lots of these things. Maybe the thing we want to do here is we want to do like some range add. So maybe plus equals 5 here. And maybe we also want to do like range sum. So what's the sum of these elements? So if we have just some array of integers and we want to do these operations, we can do both of these using a segment tree. A segment tree can handle each of these queries. For this range add, we would need to do lazy propagation. For the range sum, you can find log n different segment tree nodes. And this range is some log n segment tree nodes combined together. That's the important part. Well, a treep can do 2 other interesting things. The main one is you can take this array and split it up into 2 different subarrays. So effectively, in addition to being able to do this range add and range sum, you can take this array like this. You can find like some split point here, and then you can make this into a new array. And you can do that really quick in log n time. So that's the first use case. The second is, I guess it kind of is very similar. If you have this array split up into some different parts like this, you can join these parts back together. So you could go like that. Maybe you want to put this piece here and this piece over here. So you can very easily move these different chunks of the array around. That's kind of the main advantage of treeps. So basically, you can think of it as it's just a segment tree, but like anything you can use a segment tree for, you could use a treep for instead. The advantage is treeps have this extra ability where you can cut them up into pieces and do different things with the different pieces and then glue the pieces back together at the end. That's why treeps are so good. You'll see in almost all of the problems, they require being able to do that. So some of the problems explicitly say, well, move these pieces around. Some say do this thing, which you can look at in a different way as being move these pieces around. And in other problems, maybe they're ones harder than the set, you might find something where it's like the only way of solving the problem is to do something in some clever way where it involves or it requires, or at least it's easier if you can move chunks of the array around. Okay, so I've mentioned why treeps are helpful. Let's talk about what they actually are and how they work. The first idea that I think is very important to know about when you're dealing with a Treap is what a binary search tree is. Now, I know many of you probably already know what a binary search tree is, but just let me go over a quick refresher because I'm going to use certain parts of how they work in why Treaps are helpful. So if we have some list of numbers, maybe we have 7, 5, 2, 4, 8, and 6. I'll make all of these distinct. They don't have to be distinct, but it's easier if they are. We won't worry about the case in which they're ties. I'm going to look through these numbers in increasing order and build a tree in a certain way. So initially, we'll take just this first number 7 and we'll put it here. Then we have this next node. What we'll do is go through the tree. If we're smaller than this node, we'll go to the left. So 5 is smaller, so we'll put the 5 here. Then we have the 2. It's smaller than the 7, so we go left. It's smaller than the 5, we go left again. We put the 2 here. We have the 4, smaller than 7, smaller than 5, bigger than 2. So the 4 goes here. Then we have an 8, which is bigger than 7. So we have an 8 here. And now we have a 6, which is smaller than 7, but bigger than 5. So this is a 6. Here, we've made a tree, and each node has 0, 1, or 2 kids. The 4 has 0 kids, the 2 has 1 kid, and the 5 has 2 kids. This is called a binary tree. And there's this also nice property, I guess, where if you go from left to right in this tree, we'll see 2, like this will be the first node, this is second, third, fourth, fifth, sixth. Formally, if we do an in-order traversal, then we'll hit these numbers in increasing order. So if you have, for yourself, everything that's smaller than you is to your left in this Treap, everything that's bigger is to your right. Now, here's the important thing to keep in mind. This order of these numbers is fixed. No matter what the numbers are, the order of them is fixed. They have to be, 2 has to be the leftmost node. But the order that we put these numbers into the tree isn't fixed. If we would have put this 2 in first, then the 2 would be the root of the binary search tree, and everything else would be over on this side. So although the left to right order of these elements is fixed, the top to bottom order isn't. In other words, this tree can have different shapes with the same elements, depending on how they're inserted into the array. So what a Treap does is we say, well, sometimes, sometimes if we insert these elements into the binary search tree, we might get a binary search tree we don't like. The main example of this is if we insert the numbers in increasing order, for instance, then we would get something that might look like this. We have 1, then we insert a 2, then we insert a 3, a 4, and a 5. We get this really long lopsided tree. In this case, the height of the tree is about height n. And that's bad. We don't want that. Instead, it would be much nicer if the height of the tree was very short. So if it was about log n. Then, anytime we do one of these operations in the future, we can do it naively, just walking through each height. And that's the goal. So in order to get this log height, what we can do is we can either pick the median element each time. That's one possibility. But alternatively, if we just pick randomly, it'll be about height log n. It might be like 2 times log, but it'll be pretty close to log height. All right, so you might be wondering why that's true. The reason why is if you have some array, on average, if you pick randomly, it'll split it into one array that's about size 1/3 and one array that's size 2/3 of the array. So each time you go down, the array size becomes 2/3 minus 1 of what it was previously. If you keep taking 2/3 of a number, you'll get to the number 1 in log n steps. It's just a log n times a constant. Similarly, if you take half of a number, you get to the number 1 in exactly log base 2 of n steps. If you keep taking 2/3 of a number, it'll be log n times a constant that's a bit more. And that's the idea. If we insert elements randomly, if we pick a random order of how we insert things into this binary search tree, the binary search tree won't be that tall. It'll be pretty small, or pretty short at least. It might be wide. Cool, that's the idea behind Treaps. So we can't we don't have this whole array initially, I guess. So basically the way we actually implement Treaps is for every node, we'll give it some priority. In this case, the priority is the time that it was inserted into the tree. So 7 would have a priority of 1, 5 would have 2, this would be 3, 4, 5, and 6. What you can notice here, I'm going to draw the priorities out, is that if you look at any node, let's look at the 6 here, all of the nodes on the path to the root will have a smaller priority than it. And this should be pretty obvious. If you have some node, any node on the path to the root, it was compared to when it was inserted into the tree, which means all of those things had to be in the tree before it. 7 had to be in the tree first if you're comparing a 6 to a 7. So once we have both the priority and the left to right order, once both of those are fixed, then whatever this tree is uniquely determined. So here's the spoiler alert. In order to randomly pick the order, what we're going to do is just randomly assign priorities. So these priorities are just going to be random numbers. And if we have random priorities and we have some fixed left to right ordering, we can just cross our fingers and say, well, because this is random, the tree isn't going to be very tall, which means no matter what order these nodes are in, assuming there's like a reasonable test case generator, whatever our treap is not going to be very tall. So that's the idea behind treeps. We'll go over how to actually do those operations in just a moment. There's one thing I want to say beforehand, which is this whole thing is to avoid the problem of the binary search tree getting very, very tall. Now, we want to avoid that because when it's tall, our runtime turns into linear instead of log n. But there are other ways of solving this problem that don't use a treep. You can use something called an AVL tree. You can use a splay tree. You can use a 2-3 tree, or I guess a 2-4 tree is now a thing as well. There are different solutions you can use. Personally, I think treap is the easiest to code, and I guess there's like one particular case where you need to know a splay tree, but in general, I think treeps are the way to go. All right, cool. So we've talked about kind of the general idea behind treeps. Let's talk about how to do the specific operations. So the first one I'm going to talk about is splitting this treep up. If we have some tree already, and we know the properties are the left to right order is fixed, we don't really care what it is, and the top to bottom order, the smaller things are on the top and the bigger things are on the bottom. So we have that. Now we want to talk about how can we split this array up. Now here, when we say this left to right order, we're going to assume the left to right order is the order of the array. So this first element corresponds to the first thing in the array. This is the second thing, third thing, fourth thing, fifth thing, and sixth thing. I just want to re-emphasize that because it's really important. The left to right order in the tree, the in-order traversal of the tree, is the same as the order of the array. So one thing that means is when you're actually building your treep to solve the problem, if you want a treep that corresponds to the array in order to do stuff with it, what you can do is just make n different treep nodes that are all separate, and then you can join them from left to right, so you have your array. So you build your array with n-1 joins. You join the second thing to the first thing, third thing to the first two, fourth thing to those things. You keep merging them together until you have all of your nodes in just one node, kind of like a segment tree. Okay, so yeah, so let's say we have some array. So let's say this is our array. We'll just draw 6 different elements here. And let's say it corresponds to this tree. So we'll randomly pick, maybe we pick this as the root, this has the smallest priority. So this thing goes here. Then in its left kid, maybe this one has a smaller priority. So we have this. And then this one is here. So we have this. So this is what the left half looks like. Then in the right half, maybe we pick, let's say we pick this one here. So then this is here. And then we pick this here for this layer and this here for this layer. So this is what the treep would look like. Now, if we want to split the treep, let's say we want to split it here, that corresponds to cutting this like this. And then we want to have 2 treeps when we're done. That's the goal. So what we can do is when we're at this node, we know the size of our left kid. We can store the size of this left subtree. And then we want to say, when we split the first 4 nodes from the rest of the nodes, should the first 4 nodes are they like some part in this left half, or will this node be in the first half of the group, or will it be in the second half of the group? And then where do we go to the right half? So in this case, there are 2 nodes on the left. So this is size 2. We're at this node right here. We want to split the first 4 nodes from the last 2. we can't find 4 nodes in the left half. If we include this node here, we are still only at 3. So now what we need to do here is take this node. We want to split the first node from the rest on this subtree here. So we'll do that. Now we're at this subtree here. We see the left half only has 1 node, so we can split it here. So we'll cut this here. And the 2 things we return are the left half is this, and the right half is this here. That's how we can split the tree. Now, when we're at this half, whatever the left half was, we want that to be our new right child. So we want to make sure that when we're done, we add this edge back in. We have to make sure we add that edge as the right child. And then finally, what we'll return will be this node represents one treap, which is these first 4 nodes. And this blue node here represents another treap, which is these second 2 nodes. So we have this function, this split function, and we can split one treap into an array of 2 different treeps. So some treap, and then some like left size. And this returns 2 treeps. All right, so that's the idea behind the split function. Now we can also merge 2 treeps. So if we have 2 different treeps and we want to combine them into the same treep, we can do that as well. So it's let's talk about what the array looks like first, because I think that might be easier to think about. So if we have these first 4 nodes, and then we have 2 nodes over here, if we want to combine these two nodes, then after we do it, we'll have an array that's just 6 long, with the first 4 on the left and the last 2 on the right. Okay, so yeah, so that's pretty clear. Let's look at some example where these things have these different priorities. I'm going to draw it like this again, where the height represents the priority of some node. So yeah, okay, let's say the nodes look like this. That way it's a bit more complicated. And we'll put this node lower here. So we're going to, in this case, we're trying to join in this middle here. And this is the line that we're joining across. So first, initially, we'll try and join this node here with this node here. So we pass these 2 into our join method. And what it's going to do is say, okay, one of these nodes has a smaller priority. One of them, if this were a binary search tree, one of them would be inserted first. Whichever one that is will be the parent of the 2 halves. In this case, this is the parent. So this one is like the root, which means this one is what will get returned from this function. This will be the root. We want to make an edge here. We don't know which one we want to connect it to, but now what we want to do is join this node here with this node here. So we can recursively call this join method, and we can keep going until it's just joined into just one thing. Let's say we call the join method here on these 2. Now we want to join, I'm going to move my pointers here. So we want to join this one here with this one here. Again, we need to pick one of them to have the smaller priority. Now, each of these nodes has their priority predetermined, so we can just compare those priorities and put whichever one is smaller on top. In this case, I've drawn it so this one has a smaller priority, which means this is what will end up getting returned. So since it gets returned, we'll add an edge here. The old root needs to add an edge to whatever the new treap parent is. And after we do that, now we need to join this node here with this node here. And that needs to be the left kid of this node that we just decided was our new parent. So again, we see which one of these has a higher priority. In this case, the left of them does. So we make the left one the parent of the 2. And we want to join the following. We want to join the left kid, or the right half, with the left kid's right child. Now the right child is null. So since it just has an empty right child, if we want to join something with nothing, we just take the something. So in this case, we can finish with just this, and we'll add an edge like this. In this process, we would have deleted this edge here and this edge here. Now, if this is getting a little confusing, we'll look at code in just a minute, so don't worry too much about that. And we'll talk about actually like how it's implemented, the details of how it's implemented in just a minute here. But understanding this picture is very helpful. So we would have deleted these two white edges when we reassigned the left and right kids. And when we're done, we have a treap that looks like this. Again, the left to right order of the treap is the same as what it was before. It's 1, 2, 3, 4, 5, 6. We also know the treap in this case is 4 nodes tall, which is, I guess, maybe kind of tall. But if there were a whole bunch of nodes, the treap wouldn't be very tall because the priorities are randomly determined, which means basically it's like inserting into a priority queue randomly or inserting into a binary search tree randomly for the same reason that quicksort is n log n. In total, the height will be about log n here. Okay, so that's the idea behind merge and split. Let's talk about how the code works now. So I've written both of these in Java and C++, and this is kind of like a good demo of how the code works. I'll put the full code in the description if you want to get a link to that, and then you can look through the whole thing at once, but I'll explain it line by line here. On the left, I have Java code. On the right, I have C++. My face is covering a little bit of the C++, but you should be able to figure out what it is. It's just the same thing as the Java. And you can focus on whichever one you think is more helpful. The Java one is pretty well written. The C++ one, I'm not an amazing C++ master, so you might be able to clean it up a little bit. So my treap is going to store a couple of things. First, it stores right here. It's going to store the data in it. In this case, this was just the number from left to right. So it stores that data. It also stores the priority, which is like how high it's going to be in the treap. So things with lower priority are higher because if you convert it to a corresponding binary search tree, the things with smaller priority would be inserted first, so they'd be higher up in the binary search tree. We also store our two kids. So kids at 0 will be the left kid, and kids at 1 will be the right kid. There are also 3 values that we're going to maintain, and these 3 values will be values that are like sums over our entire subtree. So we're going to store the sum of the subtree size. So this is just the number of nodes in the subtree. We're also going to store the sum over all the subtree values. Like in other words, this is the sum of the data in the subtree. And we're also going to store this toPropagate value. So this treap will do a couple things. It'll do range sum and range add, and then also the split and merge like I talked about. When we construct this treap, we'll pass in the data, which is the value for this particular node. And we'll have the priority just be randomly assigned. In this case, I guess I don't assign the priority randomly, but you could use MT19937 or whatever to assign it randomly. Or you can use rand, I guess, but rand is not great in C++. So yeah, I guess it depends what you want to do if you're using C++. But in Java, you can just assign the priority randomly. And immediately what I do is I recalculate the value for this treap. So we'll get to recalculate in just a minute. One thing I want to mention here is usually when you do segment trees, you put the method inside of the object. So if you want to find like the subtree sum for a segment tree, then you have a segment tree class, and inside of that you have a method, which is what is the sum across some range in the node. For treaps, you can have values that are null. So if you have no left child, what I do is I store your left kid is equal to null. And in order to avoid null pointer exceptions, I don't do treap dot method. I do method and then I pass in which treap I'm talking about. That way I can handle what happens if that treap is null. I can just return like 0 or whatever I want to so that it doesn't break. And I think that cleans up the code a bit. So as one example, here's the size method. I pass in the treap. If the treap is null, I just say the size of it is 0. Otherwise, I say the treap subtree size. It's pretty simple. Okay. So what does this recalculate method look like that I talked about? I pass in some treap. If that treap is null, then I just return immediately. Otherwise, I want to set up all of the values for this treap based on the treap's 2 kids. So this treap will, in order 1, figure out what its sum is, what its subtree size is, and anything else that we want to store that's specific to this problem. In this case, all I want to do is range sum, right? And I guess like the propagate value. So I just store the subtree sum. So I calculate the size. So initially the size is 1. But then for each of the kids, I add the kids' subtree sizes as well. So I recalculate my subtree size. I also recalculate my sum, so it's my data plus however much I have to propagate, so whatever I'm going to add to my data. This 2prop is like, yeah, I guess it's just like the amount that I have left to add to my subtree. And also, when I have, when I have kids, I want to add the kids' subtree sums as well. So let's do a quick picture here. If you've got some left tree here, some right subtree here, your sum will be like the sum at your value plus the sum of the values here plus the sum of the values here. And that's what this code does. Okay, also, we have to deal with this lazy propagation. So here's a clean way of dealing with this. If we're null, just return. If the amount that we have to propagate is 0, then we might as well just like return early, save a constant factor here. Otherwise, we need to propagate this to our 2 kids. So what this means basically is if we have some value we need to propagate, when we explore some node, it's easier to think about it if that node doesn't have some propagation value we have to worry about. So we'll just push that value down to the 2 kids as soon as we look at it. And that's what this does here. So we add the amount the kids have to propagate to them, and we also update our total by the amount that we were supposed to add to this entire subtree. Finally, once we've done all of that, we need to recalculate our sum. Because it's possible these kids have now changed values, and our subtree sum doesn't include giving this propagation value to our kids. So that's why we need to recalculate for ourselves after. We also want to set the propagation value to 0, obviously, so that, because we've already accounted for it, right? We don't want to account for it twice. So now this is the implementation of the split method that I talked about. We want to split some treap with some amount in the left side. Now the left and in left will be the size of the left treap. It'll also be the index of the first thing in the right treap. That's a good way of thinking about it. Now, if we're splitting something that's null, that means we're at the very bottom, right? So the 2 halves are both empty. So we just return null and null. And then we, or otherwise, then this node isn't null, which means we want to propagate the values out of this, like I mentioned earlier, so that we don't have to worry about there being values we have to consider. We just can ignore them for now. And then we need to see, okay, well, is the split line going to come with me on the left side of it or me on the right side of it? In this first case, I'm going to be on the right side of it. So if the size of the left kid is bigger than or equal to the amount of things on the left side, that means I'm going to be on the right half of the split point. So me.kids at 0 will be this subtree here, right? So the split point's going to be somewhere like this. So we want to split this thing into 2 pieces. After we do that, we need to hook up whatever was returned on the right side of the split point to us so that our piece stays connected. So we call split with our left kid and the same number of things on the left side, and then we make sure to assign whatever our left child is to whatever the right half of the split result is when it's done. Once we've changed our node, we've changed who our kids are, we need to recalculate for ourselves. Anytime our node changes, we want to make sure we call recalculate. So we call recalculate here, and then we return the 2 pieces. So in this case, whatever was on the left half of this split point, that'll be the left half of what gets returned, and then we will be the right half of what gets returned. And this is pretty much the opposite. The only difference here is how many things, so this is if we are going to be on the left side of the split point. The only difference here, like it's just like symmetrically opposite, but the only difference is we want to subtract out the size of the left and also our position for the number of things that'll be in the left. So let's say there are 3 things here, and we want to split with 5 on the left side. There's 3 here, we're 1 thing, which means we need 1 more thing on this left side before this split point. So that's why we change the number in the left. We split along the right side, and now we set our right kid to the left half of that future split line. So this is the implementation for split, same thing in C++. Hopefully that makes sense. Okay, merge is pretty similar. So how does merge work? Well, if we we want to merge like something with nothing, then it's pretty easy. We just take this thing. If we want to merge something with nothing on the other side, again, we just take this thing. So these are these first two cases. Otherwise, we know both of these things aren't null. So we've got some stuff here with some stuff here, maybe like this. And we want to merge these two things into one group. All right. So now one of these things needs to have its priority be smaller than the other. If the priority is a tie, we'll just like not worry about that case. It might make our treap one taller than it needs to be, but we're just going to make our priorities random integers, so the chance they tie is pretty small, which means if it's one too big, it's not really an issue. So yeah, that's the idea here. But if the left priority is smaller, that means the left one should be on top. So if we want to merge these two, we pick whichever one's going to be on top. We're going to say this one's going to be on top. And now what we need to do is merge whatever this is with this. Merge these two things. We need to set our right kid equal to that. So if our left kids are on top, we merge our right kid with the right half. And that's what we set our right kid to. Of course, after we've just changed this left node, right? We've just changed its right kid. So we need to recalculate for the left node whenever we do that. And the same thing happens, or like I guess the opposite thing happens if we want to change the right node. Cool, so that is merging and splitting. Those are the two main important things. Now let's talk about how you can do interesting stuff with this treap. So we know how to merge it. We can cut it into, or we can split it by cutting it into two halves. We can also merge it by combining two halves. Now, that makes these queries way easier than what they would be on a segment tree. Doing range add on a segment tree is tricky. You have a bunch of cases. You've got like the three different cases. Either it's entirely outside, entirely inside, or it covers you. It's entirely outside, it covers you, or it intersects you. Those are the three cases for segment trees. But for treeps, we don't even have to worry about those cases. And here's why. Let's say we have some continuous range of the array, right? If we want to find, or if we want to update these nodes here, what we can do is just split the array like this, split the array like this, and then add 3 to this entire group. Once we've done that, we can just join them back together. Now you might be a little bit concerned because you'll have lazy propagation values, and when you join, will the lazy propagation values not accidentally spread to these other things? They won't. We're fine there. The reason is we propagate anytime we touch any node. So when we do our propagation, it will only impact these middle 3 nodes. The implementation for this is really easy. First, we split on the left point of the range. So everything from L and bigger will be on the right half. Everything else will be on the smaller half. After we've done that, on this right half, we have to cut off the right half of the range. So we'll cut off the range at the right endpoint. So anything from right to left will be at B at 0. Anything left of left will be at A at 0. And anything right of the right will be at B at 1. So now B at 0 is the middle portion of what we have left. And we want to add something to that, so we just increment the 2prop value of that node. We say for everything in B's subtree, we need to increment by this amount. Now anytime we touch one of those nodes, the propagation values will get pushed down that treap. So it's super nice. Once we're done, we can just merge them back together. And now anytime we look at these nodes, as long as we remember to propagate correctly, we'll have successfully added to exactly the range that we're looking for. So I also briefly wanted to talk about the runtime of all of these operations. For both split and merge, they don't have any loops or anything inside of them, but they are self-recursive, which makes them not run in order 1. But the thing to notice with these is, in both cases, when you call the method itself a second time, it goes lower down in the tree. So for split, if you split some node, when you call the method again, you'll either split its left kid or its right kid. You can only go down the height of the treap number of times. And since our treap is height log n, the total runtime of the split method will be log n. For merge, you have 2 nodes, and each time you call merge, you'll move one of the pointers down. So either you move the left pointer down or the right pointer down, depending on the priorities. And again, this is log n, because each of these treeps is height log n. You can only move the pointers down 2 times log n time in total. So we've talked about some really cool things you can do with treeps. You can do the split, the merge, and basically any sort of segment tree operation that you want. But there's also one other really cool thing that you can do with treeps. And that is the ability to horizontally mirror something. So if we have some array that looks like this, and we want to flip it so it looks like this, that's exactly the property that I'm talking about. Now, because these videos get a little long in order for me to be able to explain everything that I want to in them, I thought a change in scenery might be nice. So I've come up with some mostly unnecessary demo outside in the Wild West. I'm in Seattle right now, and in 2020, Seattle is basically the underworld. So because of that, all of the trees are upside down. For real trees, the root's obviously on the top and the leaves are on the bottom. But here we have this tree that I found, which has the root on the bottom and the leaves on the top. So we've got the root right here. I've just taped a juggling ball to it. Then we have another node over here. It's a leaf node, another node over here, and then one node here and one node here. So that's the tree that we're working with. If we want to flip this tree around, we can very simply do it in order 1 by walking to the other side. So now we've mirrored the tree, and we've done exactly what we've tried to do. This might seem pretty obvious, but there's an interesting thing that happens here. We've modified every node in this tree in the same way. For every node, this direction's north. What used to be the edge to the north, that used to be the right edge, but now the edge to the north is on the left. So for every node in the tree, we've changed what used to be its left kid to be its right kid, and vice versa. Now, why is that helpful? Well, we can do operations to an entire subtree pretty easily. We know how to do that with segment trees. We can do it with lazy propagation. And with treeps, we can do the same thing. So if we know that we're going to modify an entire subtree of some node, we can just store some value. And if we ever go to the kids of that node, we can propagate that value down to its kids. Then when we reach each kid, the first thing we'll do is if we need to flip the 2 kids, we'll immediately do that. Then flip the two edges. So we'll flip maybe this edge and this edge if we need to. And we can do that easily. So by doing that, that lets us flip an entire array if we need to, or really an entire subtree of one node. Now, that isn't helpful for segment trees, because for segment trees, the range you want to flip might not correspond to just one node. You might want to flip, for instance, this node here, followed by this entire subtree. And you can't do that because that's not the subtree of just one node. Well, with a treep, if we want to flip any continuous range in the array, we can do that very easily just by cutting this edge off. And now we can flip that range because this is an entire tree by itself. So we can do a slice here. And now we have the part of the array that we're looking for. We can mirror that using lazy propagation. And then when we're done, we can join these 2 back together. So just to clarify on that reflection one more time, if you have some subarray like this, if we want to mirror just these elements, we split here, and then reverse all of the elements in the middle. We want to reverse all of them, not just some continuous range. Since we're reversing all of them, that's something that isn't that hard to do. Then once we've done that, we join them together, and lazy propagation will take care of the things in the middle getting flipped and the things on the left not getting flipped. That's exactly what we want. All right, awesome. So we've talked about lots of really cool things you can do with a treep. There's one more thing that I should talk about, which is, I guess, how can you implement this reflection? Well, it's pretty easy. We'll go back to this code example that I was talking about. And all we have to change is this propagation value. So here we can store any propagation values we want. We should also store, in this case, whether we want to flip our subtree. If we do want to flip the subtree, then in this propagate method, we have to do additional stuff. So the first thing is, if our toProp is true, we want to swap our left and our right kids. And also, if 2prop is true, we should flip the 2prop values of both our left and our right kids as long as they're not null. So yeah, that will propagate the flipping correctly. And every time we look at some node, we immediately propagate. So that way we won't introduce like propagation to other nodes when we join them. Okay, fantastic. One last thing that I want to talk about, and that is finding the parent of a treap. So it's probably helpful. Like the way I usually code up treeps is initially I just have a bunch of nodes. I make one node for every element in my array. And the first thing I do is I join them all together. So now I have some array that looks like this. Now it might be the case that in the process of me solving the problem, I split this array up into different parts, and I wind up having something that looks like this. Like I just have some different parts lying around, I guess, in different parts of memory. But I might know, all right, here's the first treap, the treap with index 1. Here's the treap with index 2. Here's the treap with index 3. Somehow I know that they're like this. Maybe this is the treap with index 4. Here's the treap with index 5. Here's the treap with index 6. I'm drawing these as an array. In reality, they would be in a tree structure. So you might have a tree that looks like this. That might be one tree. This might be the other tree. Now what I want to do is, it's probably helpful for us to be able to find the root node, the root like treat value for each one of these values that we're interested in. In order to do that, we can just also maintain what the parent is. So we can maintain a parent pointer, and anytime we change the kid pointer for some node, we also have to update the parent pointer for that same node. In the code, I'll go through those positions. So yeah, in the constructor, we don't have to worry about anything. Size, we also don't have to worry about anything. This recalculation, we don't change anything. Nothing gets changed. All that gets changed is like our aggregate values. So we don't have to worry about this as well. Propagation value, again, the tree structure doesn't change. All we're doing is looking at our two kids and then calculating aggregate values and adjusting them, I guess. But the structure of the tree doesn't change. Now, split and merge are the two things where we have to maintain the parent pointers correctly. In this case, when we set me.kids at 0, then we have to set leftRes at 1.parent correctly. We have to remember to do that. We also have to say we're going to split this thing from this thing. So whatever me.kids at 0 used to be, its parent is no longer us. Its parent might be null. So we have to adjust that accordingly as well. And then same thing here. Like we've got similar but opposite examples. And in this merge method, also we're adjusting what our kids are. So we have to make sure we modify that accordingly. Every time we adjust one of our kids, we have to say the previous thing is no longer our kid, and whatever our kid now is, or our previous thing's parent is no longer us. And whatever our new kid is, his parent now is us. All right, fantastic. So the last thing I want to say is just some quick warnings with these. You have to make sure, you have to be very careful, all of these methods return the new treap head. So a really common bug is to call one of these methods, but forget to use its result. So you might want to merge two treeps, that's fine. You have to remember to set whatever your root treep is to the result of that method call. Now that's true with merge. It's also true with split. When you split it, you now have two different nodes. So you have to make sure you use those and you don't use treat values that are not returned from these methods. And those are like the only two cases where the actual structure of the treat changes. So just whenever you call those two methods, be very careful not to ignore the result. All right, well, thank you for watching. I hope you enjoyed. Make sure you try the problems on the Codeforces Gym. I think they're very interesting and you'll probably like them. And that's all I have for today. So I'm gonna act like a treep and split.